Hi all, welcome to my presentation on numerical wind tunnel testing and challenges. Before I dig into cool stuff, let me introduce myself. I am Sunit Surya, a doctoral researcher at Chair of Structural Analysis, Technical University of Munich. My main supervisor is Professor Kai Webb-Pletzinger, and my mentor is Professor Roland Wuschner. Technical University has provided a great environment for my doctoral studies because of the constant guidance and advices from my supervisor and the mentor. Not only that, the colleagues around me also had provided great support to continue my doctoral studies. So my focuses are turbulence modeling, butterfly effect, optimization, and adaptive mesh refinement. So as you can see, they are a little bit of technical. So I'm not going into technical details of any of these topics, but I will introduce a small example problem which explains what I'm doing and then dig into a little bit of technical details. Before going to that, I'd like to show you this right downmost picture. So it's one of the coolest things in TUM. So it's a slide which is 3 stories high, and then I loved it very much. If you are here by any chance, I recommend you to try it out. It's really nice. So enough of that. Let's go into the details. I would like to take this opportunity to thank International Graduate School of Science and Engineering because they were funding my whole doctoral time period at Technical University of Munich. Not only funding, actually, they were providing me with guidance as well as courses for soft skills to improve myself as a researcher as well as a presenter. Also, they were 2 times winner of the German Excellence Initiative, and they provide financial support and guidance for international projects as well as multidisciplinary projects. I am under the ATMOPACE project, which is 12.01. The long name for it is Filtered Adjoint Based Techniques for Mesh Optimization to Enable Predictive Wind Field Assessment in Complex Environments. I know that is too long and too hard to pronounce even. So let's dig into the simpler stuff now. I am mainly working on wind. So what is wind? From the leftmost video, you can see a sandstorm, which is governed by really high-speed wind velocities in a desert. So they can span up to a few hundred meters to a few kilometers depending on the situation. Next one, you can see a snowstorm. It is also governed by wind, and both of these situations can make our lives a little bit uncomfortable wherever we live in. So we need to understand what are the causes of these phenomena. In order to understand that, we need to look into the complex urban cities which we are living in, because these structures in a city governs the wind flow around the city, and the topography is also actually contributes towards it. So these 3 ingredients makes wind a really a complex phenomenon to study. So why is it important to study wind? From the leftmost video, you can see a pedestrian crossing in a Norwegian city. At that time, they had really high wind speeds, and then it was even really hard to cross the roads, and it made the life really uncomfortable for them at that time. But it was still, at that time, it was not that dangerous. But let's look into one of the dangerous situations. In the middle, you can see a Danish wind turbine acting under high wind speeds. So you can see after some time it just collapses and all the wind blades are flown away. And if someone was near that region, yeah, they could have heard. But for lucky for us, no one was near in that region. In the rightmost one, you can see the famous Tacoma Bridge collapse. So you can see at that time engineers were not actually paying attention to wind effect on structures, so they designed the bridge. But then when wind acted upon it, it starts to oscillate. These oscillations actually continues to collapsing of the bridge as in here. So you can see this is really dangerous, and we need to understand these phenomena better to design better structures. So let's look at how we can predict these wind fields. So the leftmost video is actually a wind tunnel test. So what we're doing here is actually we scale down actual cities structures into small scales, and then we put it inside a real tube like a structure, and then we use high-speed fans to replicate wind effects, and then we measure pressure and velocities by using some specific measurement units inside this downscaled structures. In the right side, you can see how wind tunnels are used in car industry, which is one of the famous ones, and I'm also interested. So in there, you put the real scale car, and then you actually force it to have some fan blowing wind on it, and then see how the wind is blowing on top of the car. And then this is important for the car industry because they can make decisions on how to improve drag and lift so that they can have fast cars. But one problem is there in all those wind tunnel tests, that is the cost, because as you have seen, we need to make prototypes, which is really costly, and we need high initial investment because we need high speed fans and all those investments. So in order to reduce the cost of these tests, we can do numerical wind tunnel testing. So what we do here, we take actual cities, and then we do some simplifications and modeling inside a computer to arrive at the rightmost video, which shows velocity field distributions over this nice Barcelona cathedral. So how do we do it? That's the next question. First, what we do is simplification. What do we mean by simplification? So we have this cathedral which has a lot of details, but if we are to actually simulate all of these details in a computer, even the fastest supercomputer won't be enough for us. So what we do is actually we make simplifications based on engineering decisions. So this simplified, as you can see in the middle, the cathedral is simplified to a cylindrical structure. This is just an example only. And then we do sometimes further simplifications, like this 3D cylindrical structure is simplified to 2D cylinder, because this makes the computational effort really reduced, and so that we can do more and more testing with different parameters. Once the simplification is done, so the problem is how important are these simplifications to whatever we want to do. Like, what are the repercussions of these simplifications, and how do we do these simplifications? That's the question. Then we have discretization. So once we do the simplification, we have to do domain decomposition. That means we have to divide this right hand side image into smaller domains so that we can use some form of equation to actually predict the wind or the flow on that small element. But the question is, how are we going to do it? Because where to do a lot of elements, where not to do it, because having a lot of elements of course will increase the accuracy of the solution, but it adds on to the computational complexity, which sometimes is prohibitively expensive. So we need to be smart in that. So how to do it? That's another question. Then the final one is actually the formulation. So I was talking about small elements like these triangles. So what kind of equations do we use to solve wind field in these small elements? That's the next question. And what are the drawbacks in each formulation? So my PhD work is actually focused on all these three questions mainly. How to have effective solutions for these three. Let's look at the first one. How to simplify. So in the leftmost video, you can see a man actually having a water flow through a nozzle. So as you can see, when he changes the nozzles, rotates it, the flow differs, flow changes. So that means the flow is actually sensitive towards the changes in this rotation. That is called the sensitivity analysis. So this sensitivity analysis is really important in decision making, because if you want to design a new structure or something, if you know how sensitive it's gonna be for one of the wind parameters, then you can have better designs. That's one of the applications of this sensitivity analysis, which is one of my PhD work. So what are the challenges in this sensitivity analysis? First one is actually, we are not talking about these nozzles, we are talking about the urban cities. So they are really complex, and then you need, as I showed you in earlier, a domain decomposition which is really large. So we need to think about how to do it in several computers than one computer, because one computer won't be enough to solve each of these elements. It will take years to solve. The other one is actually the butterfly effect. Maybe you have heard about it. So let me explain it in briefly. Butterfly effect is the sensitivity towards whatever your starting conditions is. As an example, in this nozzle case, so let's say that your temperature is different in this day. So your flow pattern will most probably will change. So that means your atmospheric conditions also affect this flow pattern, not only this nozzle rotation. That means whenever you want to do sensitivity analysis for the nozzle rotation, you need to take into account that atmospheric changes and how does they affect also. That's a challenge. I'm not going into details of it, so I will stop at that point. So what are the applications of this sensitivity analysis? As I told you, this can provide designing insight, so you can do better designs. The other application is optimization. So what is optimization? So once you have this sensitivity information, so let's say this rotation of this nozzle, so you can design better nozzles to have better flows for whatever the purpose of you want to use it. That is called an optimization process, and we can make it automatic. So we get automated designing process altogether. Other one is robustness estimation. So if you want to have the same flow pattern for small changes, so you can actually calculate the robustness of this one. So this is not robust, actually it changes a lot when you rotate it. So but sometimes you need robustness also. So these three applications can be done when you have sensitivity information about whatever you want to calculate. So let's look at one of the examples of optimization process. So you can see in the right top two figures the initial design. This is a 2D flow problem. So the flow is flowing from the left to right, and then there's this geometry inside. So what I'm trying to optimize in here is actually the aerodynamic quantities like lift to drag ratio. So let's see how it goes. So when the optimization is starting, so each design iteration actually is giving you sensitivity analysis so that you can have a better lift to drag ratios. So from the left side graph, you can see how lift to drag is changing with iterations. That means each design. So it's increasing. That means we are getting better and better designs for lift to drag. So this sensitivity information helped us to obtain a better design in this optimization problem. Next part of my doctoral research is actually how do we do the discretization, because it involves a lot of human effort, because the engineer needs to decide where to put more small elements and where to put large elements and where not to do anything. So what I did was actually, so this decision making is automated as much as possible. So most of the time when we do a numerical wind tunnel testing, we are interested in an objective such as how much drag do I see in around the cylinder, in this cylinder case. So the wind is flowing from left to right. How much drag do I see? And what is the accuracy of whatever I calculate from the numerical wind tunnel? So based on that, I calculate the error sensitivities of this drag calculation in this problem. And let's say that I want a 50% error, so I get this kind of a decomposition. Let's say I only want a 1% error, so I get this kind of a decomposition. Like that, this domain decomposition can be automated based on whatever you want and how much accuracy do you want it. This is part of my thesis as well. Finally, we can think about how do we formulate. As you can, as I showed you in earlier slides also, in the top also. So when we have small elements, we need to think about what kind of equation, or like how do we formulate, because we have some inputs and we need to do something to get the outputs, like the wind, how the wind is. So from this table you can see for different types of formulations you get different types of wind fields for this rectangular flow around problem. It is important to know that what are these differences, because if we are going to make some decisions based on this, we need to know what are the drawbacks of each formulation and what are the advantages of each formulation and how to be efficient in whatever the use case we want. So this is also part of my thesis. So up to now I have introduced what is wind and how important it is to investigate wind and how do we investigate wind. Two different methods, like the wind tunnel test and a numerical wind tunnel test. But my research is focused on actually how to make the numerical wind tunnel testing efficient and effective. The challenges which I faced is actually how to tackle the butterfly effect, because the sensitivity is calculated in a really a wind simulation is not useful. So I need to have a stabilization method for that, and running on many computers, because our wind simulations are really large and complex, so we cannot use only one computer to solve them. So we need to use a lot of computers like supercomputers to solve them. So how to make methodologies which can run on them and how to make them efficient, also one of the challenges. So my PhD was focusing on these things and how to deal with these and make answers for them. Thank you for all. If you have any questions, just put them in the comments, so I would be really happy to answer them. Thanks a lot and have a nice day.